In this lesson, we'll explore sigma notation and using Riemann sums to compute areas. We'll begin with some summation formulas. Our first formula tells us that the sum from k equals 1 to n of c is equal to c times n for any constant c. Let's take a look at what this means with an example. So here we have the sum from k equals 1 to 4 of the constant 3. So here our c is equal to 3 and our n is equal to 4. So remember from our sigma notation that this just means 3 plus 3 plus 3 plus 3. So for each k we get the number 3. So we have 3 plus 3 plus 3 plus 3. Adding this up we get 12. Now let's look at this in the context of our formula. Again, c was 3 and n was 4. So our formula tells us that this should be c times n, or 3 times 4, which is in fact 12. So this formula is telling us, so the sum from k equals 1 to n of c, remember from our sigma notation, this just means c plus c plus c plus c for k equals 1, 2, 3, 4, etc. And we stop when we hit k equals n. So here we have n terms in this sum, or we have n c's here, so this just becomes c times n. So the sum from k equals 1 to n of a constant is just that constant times n. Our next formula is the sum from k equals 1 to n of k. And again, our sigma notation, remember this is equal to 1 plus 2 plus 3 plus 4, and we stop when we reach n. Our formula tells us that this sum should be equal to n times n plus 1 over 2. Now we're not going to prove here that this formula is true. Instead, we're just going to explore this formula again by looking at an example, and we'll prove separately why the formula is true. So in our example, we have the sum from k equals 1 to 5 of k. So our n here is 5. Remember what this means. When k is 1, we get 1 plus 2 plus 3 plus 4, and we stop at 5 because our upper limit of summation here is 5. Adding these numbers up, we get 15. And now our formula tells us, so our n was equal to 5, so our formula tells us that this should be equal to 5 times 5 plus 1, which is 6, all over 2. Let's check that. So 5 times 6 is 30 over 2 does in fact give us 15. The next formula we'll look at is the sum of the first n squares. So again, remember from our summation notation, this means 1 squared plus 2 squared plus 3 squared plus 4 squared, and again we stop when we reach n squared. So our formula tells us this should be equal to n times n plus 1 times 2n plus 1 all over 6. Again, we're not going to prove this here, but we will look at this in context with an example. So here we have the sum from k equals 1 to 5 of k squared. Writing this out using my definition of sigma notation, this gives us 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Now go ahead and add all of those numbers up, and you'll get 55. Now let's look at it in the context of our formula. So here n is equal to 5, so our formula tells us that this should be equal to 5 times n plus 1 is 6 times 2n plus 1 is 11 all over 6. So let's check that. The 6's cancel. We do indeed get 5 times 11, which is 55. So again, we haven't proven this formula. We'll want to use these formulas in context as we're solving problems, so we're just looking at them here in terms of particular examples so that we understand how to apply and use these formulas later. I will give you these formulas if you need them on a quiz or an exam. Let's look at one more formula. So here we have that for any constant c, the sum of some constant times an expression involving k is equal to c times the sum. In other words, you can pull a constant outside of your sum. Again, let's look at an example. So here I have the sum from k equals 1 to 5 of 3k. So here my c is equal to 3. My expression a sub k is just k, and my n is equal to 5. Now again, let's just write out what this means. So when k is 1, I get 3 times 1. When k is 2, 3 times 2, etc., up until 3 times 5. And now what I'm going to do is notice that every term has a 3, so we can pull a 3, factor a 3 out of all of our terms, and we get 3 times the quantity 1 plus 2 plus 3 plus 4 plus 5, which gives us 3 times 15, or 45. And notice that pulling this 3 outside of the sum is exactly what we wanted to be able to do, that the c, or the constant, can come outside of the sum. And that's precisely because if you have a constant in every term, then you can just factor that constant out from every term in your expression. So 3 times the sum from k equals 1 to 5 just gives us 3 times 1 plus 2 plus 3 plus 4 plus 5, which is, of course, the same thing, 45, as we get when we just expand this out. So the key idea from this last formula, again, is that anything that doesn't depend on k, so anything that's a constant independent of k, can just come outside of our sum.